Hello everybody, and welcome to the first installment in a series that will hopefully take us through all of SACE Stage 2 Physics. To get the ball rolling, I will start with projectile motion, the topic involving the most rolling balls. Many of you watching may be familiar with both how many puns I make and the majority of the content covered in projectile motion from undertaking physics last year. Projectile motion can be broken into two components, a horizontal one and a vertical one. This is because in year 12, you get access to all two dimensions of motion. Yes, that's right, you've been lied to. All that time you've been told of only one spatial dimension when there are actually two. Makes you think of what other dimensions physicists are hiding from you. The idea of horizontal and vertical components is actually quite straightforward. If we have some object that I prepared earlier and give it a velocity, then the components of that velocity are just the lines that are drawn to make the velocity vector into a triangle. Since we know the velocity, which includes both the speed and direction, we can use trigonometry to find the other sides. This means that the vertical component is the speed times the sine of the angle, and the horizontal component is the speed times the cosine of the angle. This isn't limited to velocity. The same logic of breaking down motion can be done for any vector quantity, such as displacement, acceleration, force, or momentum. The reasons for splitting the vector is that orthogonal components do not affect one another, just as jumping up or down, a change in the vertical component, does not make one move side to side, a change in the horizontal component. This is incredibly useful. This allows us to use the Suvat equations for motion in one dimension to find out how things move in two dimensions, just by solving each component. If we can find out component velocities or any other vector components, we can solve for the overall velocity or vector quantity by using our favourite triangle-styled solver by Pythagoras to find the magnitude, and the much less popular inverse tangent function to find the angle. We can see this better given an example. If we have an object which has a horizontal velocity of 4 meters per second and a vertical velocity of 3 meters per second, then the speed that the object will have will be the square root of 4 squared plus 3 squared, which is the square root of 9 plus 16, which is 5 meters per second. To find the direction, we use TOA, a good friend of so and car. In this case, we know that the opposite side is the vertical component and the adjacent side is the horizontal component. To find the direction, we rearrange to get theta on its own, and then we can substitute the values of 4 and 3 into the equation to get a nice round 36.869897 degrees. Anyways, this gives us a velocity of 5 meters a second at an elevation of 37 degrees to the right. With the understanding of horizontal and vertical components now built, we can look at how the equations of motion are used to solve for motion in one dimension. If you have done year 11 physics, then you should be familiar with these concepts. To derive these equations, we need to understand how displacement, velocity, and acceleration interact with one another. Displacement is distance with a direction, a vector quantity that is measured in meters. Time is a scalar quantity, measured in seconds. For a good example of how time works, check the red bar at the bottom of this video. Velocity is a vector quantity that measures the rate of change of displacement with respect to time. It is measured in meters per second. Acceleration is the rate of change of velocity, fun, and is measured in meters per second per second. If we continue on this trend, the rate of change for acceleration is called jerk, followed by snap, crackle, then pop, because physicists like rice bubbles. To derive these equations, we will work under the assumption that acceleration is constant. Starting off, we can define average velocity as displacement over time. Shocking, I know. An average velocity is equal to half of final velocity, v, plus initial velocity, u, as that is what an average is. This means that we can combine these equations to create a new equation without that ugly average velocity in it. If we multiply both sides by t, then we can create an equation which gives us displacement when both velocities and time are available. We can call this equation 1. Acceleration, being the rate of change of velocity, can be expressed as a change in velocity over a change in time. A change in velocity would be equivalent to final velocity minus initial velocity, so we can substitute that back into the equation. Now, if we multiply both sides by t, we can remove that fraction And if we do a bit of rearrangement, we can find that final velocity can be given as initial velocity plus acceleration times time. This is equation number 2. If we graph equation 2, we can see something interesting if we put time on the x-axis and velocity on the y-axis. Our initial velocity will be our y-intercept, as that is the velocity when time is equal to 0. And acceleration will be the slope of our graph, as it is the rate of change for our velocity. Since our acceleration is constant, the line will be drawn straight. The cool part of this graph is that it can be used to find displacement. What? Since we know that displacement is given as average velocity times time from the rearranging of the first equation, we can use geometry to solve for the displacement. This only works though because our shape has one side that is velocity and another side that is time, allowing for us to calculate displacement as the shape's area. Back on the graph, we can see that the shape can be split into a rectangle and a triangle. The rectangle, which has an area of base times height, which in this case is TU, and the triangle has an area of half base times height, which is half AT times T, or half AT squared. This means that displacement would be equal to UT plus half AT squared, the total area under the graph. This is equation number 3. The final equation that will be derived is one where time will be eliminated and will come from equations 1 and 2. To remove time from these equations, they will be rearranged so that they solve for time, both of them. For equation number 1, this means dividing both sides of the equation by half initial plus final velocity, and for equation 2, isolating the AT term and then dividing both sides by acceleration. These equations can then be smashed together as they both equal time, removing it from the new equation. To make this equation a bit neater, both sides can be multiplied by a and then by v plus u. This gives us 2as on the left and v minus u times v plus u on the right. The right-hand side can be simplified further as the brackets expand to the difference of 2 squares. Finally, the equation can be rearranged to make velocity squared, thus the subject giving us equation 4. With these equations in hand and an understanding of motion in 2 dimensions, it should now be possible to tackle any problem in projectile motion. Just remember to calculate each component individually using the component formulas to switch between them. That's all from me today, and remember, physics on. SACE Stage 2 Physics. I set the teleprompter speed too fast. Anyways, this gives us a velocity of 5 meters a second and a elevation of 37 degrees to the right. Did I just say elevation? I did just say elevation. I'm going to do that again. The speed of the object will have the square root of 4 squared plus the square root of 3 squared. Never mind, that's not correct. Do not say square root twice. Where time will be eliminated. And the teleprompter is again too slow because I didn't fix it.